In this first part of the momentum chapter, we want to look at the concepts of momentum and impulse and do some basic problems with the impulse-momentum theorem. Momentum and impulse, the impulse-momentum theorem, actually comes out of Newton's laws. We start with Newton's second law, F net equals ma. And then we look at the relationship of acceleration. Acceleration equals change in velocity over time. Now, if you put these two together, you can get F equals m times change in v over change in t. So we replace acceleration with change in velocity over change in time. Cross multiply to get rid of the denominator here, and you get F times change in t equals m times change in v. And that is actually the impulse momentum theorem. Force times change in time equals mass times change in velocity. Now you can break that apart into two portions. Time is going to be one of the key features here, and this is where time plays into force, mass, and velocity. Many of these problems can be solved using Newton's laws, but we're going to see here with collisions that momentum and impulse can be very useful tools for looking at the problem. As you look here, mass times change in velocity. If you have something colliding, hitting something, the change in velocity is going to be the same regardless of how it hits. The time is going to end up being the really important key component. If you can increase the time it takes for a collision, you will decrease the force. And that's why airbags work the way they do. That's why seat belts. That's why padded dashboards. That's why the crumple zones in your car are all designed the way they are to increase the time that it takes for you to come to a stop, therefore decreasing the force. Let's be very specific with the airbag. The airbag, when you're in a collision, pops out. You hit the airbag and come to a stop over a much longer period of time than you would if you hit the steering wheel. Hit the steering wheel, you're going to come to stop almost immediately. Airbag has a lot of give to it, so you can come to the stop over a much longer period of time. Now we're talking much longer in fractions of a second, but it's 2 to 3 to 4 times longer than it would be without the airbag. By having that additional time, the force goes down by the same amount. So if it takes 4 times longer to stop, you'd have 4 times less force on you. By decreasing the force, you therefore have less of a chance of being injured. Impulse is one piece of this. Impulse is the force times change in time. It can also be equal to mass times change in velocity or change in momentum. So you can break this equation down a lot of different ways. Impulse equals force times change in time. We know momentum equals mass times velocity. So the change in momentum is the mass, which isn't going to change, times the change in velocity. So we can set any of these things equal to each other. Force times change in time can be equal to change in momentum, or mass times change in velocity, or J. It all comes together. To have a change in momentum of an object, you must have an impulse. In the lab, what we're doing is we're measuring the impulse with the force sensor, taking the force and time graph. When we have a force versus time graph, think about area. Area is found by doing, say for example, a triangle, half base times height. So when you had your graph, you got this peak, we can find the area. The base variable is time. The height variable is force. So force times time was what we used to find the area. And force times time is impulse. So the area under a force versus time graph will also give us impulse. And that's what we're doing in the lab. We're finding that area to get the impulse. And then we're comparing that to the change in momentum of the cart as measured by the motion sensor and seeing that those two should be the same. Most of you are getting percentages less than 10%, which is very good. Momentum is the mass of an object times its velocity. We use the letter P. So another way of writing the impulse momentum theorem would be F delta T equals P final minus P initial, or change in momentum. So there's lots of different ways to write this. F delta T equals delta P, or F delta T equals M delta V, or F delta T equals mv final minus mv initial. All ways of writing the exact same thing. The basic equation for momentum is mass times velocity. Mass is in kilograms, velocity is in meters per second, so the units for momentum are kilograms times meters per second. Newtons times second is also the same thing, and if you think about a Newton is a force variable. So if we do F equals ma, mass is in kilograms, A is in meters per second squared. If we multiply that by seconds, that gets rid of one of these, and you get kilograms times meters per second. So newtons times seconds and kilograms times meters per second are the exact same units. And remember, momentum is a vector quantity. It does have a direction just like velocity, so it can be positive or negative. As you saw in the lab, when it bounced back up the track, you had a negative velocity and a negative momentum. Now we're going to go through some basic problems using impulse and momentum. These will get more complicated as we continue through them. This first one's pretty straightforward. What is the impulse if a 10 Newton force is applied for 8 seconds? Now, we're looking at force and time, so I can do impulse equals force times change in time. So the impulse is 10 times 8, which is 80 Newton seconds. Second one, what is the change in momentum if a 10 kilogram mass accelerates from 8 meters per second to 20 meters per second? So we know the mass, 10 kilograms, the initial velocity, 8 meters per second, and the final velocity, 20 meters per second. We're looking for the change in momentum, so that's going to be final momentum minus initial, which will be the same thing as mass times final velocity minus mass times initial velocity. Or you could write this change in momentum as mass times change in velocity. So in here, our change in momentum will be 10 times 20 minus 10 times 8. So our change in momentum, 200 minus 80, which is 120. So momentum in this case is change in momentum 120 kilogram meters per second. What is the impulse of a 15 kilogram mass sliding at 14 meters per second is stopped? Remember, impulse is the same thing as change in momentum. So if we can do impulse, we can do mass times change in velocity. So the impulse here is the mass, 15, times the change in velocity, 0 minus 14, since the final velocity is 0 here. So we'll do 15 times negative 14, which would be negative 210 Newton seconds. Next one, if an 18 kilogram ball traveling at 18 meters per second is made to go 19 meters per second the other direction by a force exerted for 3 seconds, what is the average force on the object? So let's list out the variables we know. Mass is 18 kilograms. Initial velocity is 18 meters per second. Final velocity is negative 19 meters per second. This would be the key area where I expect people to make a mistake on this problem, or I've seen a lot of mistakes, is forgetting that if we're going in the opposite direction, we must make it negative. And the time is 3 seconds. Now here's where the impulse momentum theorem altogether would be very useful. We're looking for the force. We know the time is 3. The mass is 18. The final velocity is negative 19 minus the initial velocity 18. So negative 19 minus 18, negative 37. So F times 3 equals 18 times negative 37. F times 3 equals negative 666. Divide that by 3, and we would get a force of negative 222 newtons. It should make sense in that case that this is going to be negative, because to cause the ball to go in the opposite direction, we'd have to exert a force in the opposite direction. 1,500 kilogram car traveling at 25 meters per second comes to a stop in 12 meters. What is the impulse on the car, and what is the force on the car? Now this gets a little bit more challenging. 1,500 kilograms, initial velocity of 25 meters per second, final velocity of 0 meters per second, a distance 12 meters. Here we can find the impulse by doing mass times change in velocity. So 1,500 times 0 minus 25. Which means we'd have an impulse of negative 37,500. Kilogram meters per second, or Newton seconds. That's the first part. Now we're looking for the force. So we need to know the time it takes to come to a stop. To do that, I'm going to use one of our previous formulas. We have the delta x formula. We have that formula. All of these formulas, though, require acceleration. Remember, we have one other formula. Delta x equals half vi plus vf times t. So 12 equals half 25 plus 0 times t. So we get 12 equals 12.5 t. 0.96 for t. 96 seconds. And now we can do impulse equals f delta t. The impulse is negative 37,500 equals f times 0.96. We get 39,062. Okay, so a number of different problems that allow us to look at momentum and impulse. And you can also solve many of these problems using Newton's laws, which is what we learned in the first semester.